So hello and welcome to your final project of the quarter. This is the last assignment in mobile robotics and it is a big one. The final project is all about navigation competencies. When you study navigation, you look at things like where am I going, how do I get there, what does it look like? Where am I is localization. Where am I going is path planning and path following. What does it look like when I get there is mapping. So those are all the things that you're going to be doing for the final project. Your final project grade will be based upon how many things you accomplish, right? The more things you do, the higher your grade. There is an optional last level that will be extra credit, but most importantly is for you to try your best to get as much done as you can. And the entire final project, including demos, whether in person or videos, and the code, and the final report, it's not a worksheet or memo this time, it is a full technical report, are all due by midnight on the Sunday of finals week. By midnight means 11:59 p.m. Please watch this whole video in entirety, maybe 2 or 3 times if you need to, and then come and ask me if you have any questions. Let's get started. So the objectives for the final project are: students will use wireless communication to teleoperate their robot and for bidirectional communication, such as reading sensor data and sending out sensor data or displaying maps. Students will also create a graphical user interface to send data to the robot and display data received from the robot. The next objective is students will use range sensor feedback to create path following and path planning algorithms on their mobile robot. Students will also use sensor feedback to localize a robot in an artificial world and plan a path through it. And students will use sensor feedback to create a mapping algorithm of a world and then plan a path through the map that was created. Specific tasks include mounting an IMU and encoder to use for odometry sensor feedback along with the stepper motors, to mount Bluetooth module for wireless or serial communication, or if you can't get the Bluetooth module working, you can do it with either transceivers or game controller. Create a graphical user interface for bidirectional communication between the robot and team laptop. Program the robot to do topological path following. Program the robot to do metric path planning and then path following. Program the robot to localize in a known world. Program the robot to map in an unknown world. And program the robot to simultaneously localize and map in an unknown world. Note that the path following, path planning, localization, and mapping must all be done in an occupancy grid as well as a topological map, and we will talk about what the difference between those two are. So if you have not already, one of the first things you want to do is to mount the IMU onto the robot by connecting it to the Arduino Mega and downloading the MPU 6050 library, and then use the example to display yaw, pitch, roll data on the serial monitor. Use this example to display the accelerometer XYZ data, and then think about how you can use this data along with the encoder in order to correct for odometry error. Odometry error will become very important as you try to use this to localize the robot as well as for path following and path planning, because as error accumulates, that now will affect your ability to be able to accomplish these tasks. Then you want to mount the Bluetooth module for sending and receiving data. Connect the Bluetooth module to power, connect RX to TX and TX to RX, or hardware or software serial on your Arduino Mega. And then you're going to send code such as the blink and LED code or the HC05.INO code that I have given you an example of in the folder, and use those in order to confirm that you're able to send and receive data for the Bluetooth module on the robot. This is not always easy. It can be a little buggy. So I highly recommend that you start with the robot tethered and connect to the Bluetooth with everything tethered and make sure it all works correctly. And then once you know that tethered works, try to do it wirelessly. I do have some videos on the YouTube channel of me doing this. Note that the key is not connected. So the main things that you need to have connected are VCC, ground, TX, RX, and state. So if you cannot get the Bluetooth working, you can do this with a wireless transceiver. Here's an example of the transceiver where the transceiver is connected to an Arduino Uno on your laptop, and then on the robot is the other end of that transceiver, and they talk to each other. So this one requires a little bit more equipment, but if you cannot get the Bluetooth module working, then the way to do it is to connect the Uno and the transceiver to your laptop and have that transceiver talk to the transceiver that's connected to the Mega on the robot. If you cannot get the Bluetooth or the wireless transceiver working, you can remotely drive your robot by using the PlayStation controller. You will have the game controller in your hand and then have a Bluetooth dongle wired to the robot. And you can use this for teleoperation for things like localization and mapping. This is not ideal because it does not give you a way to then receive data back for your GUI. So by doing this, there's no way to update the graphical user interface with the map, with the sensor data, etc. So then you're going to have to come up with some kind of serial communication, such as some kind of wireless way to display a map in your serial monitor. So what is an occupancy grid? An occupancy grid is a map of the world where it is separated into cells similar to a matrix, which is why we use a matrix to describe our worlds, where every cell is either occupied or free. If it's occupied, we use a 99. You can use whatever number you like. And if it's free, we use a 0. In this case, that green S represents the robot's starting point, and the blue G represents the goal where the robot is trying to get to. So one of the test beds that we use is this one shown here, where our artificial world has some occupied and some free spaces. One of the challenges you're going to see here is that now we have a wall in the bottom left that separates the robot from the goal position. And if we did this with just an occupancy grid, such as 0s and 99s, then that cell where the goal is located would be completely blocked out. So this is why we need another way to also represent worlds other than occupancy grids, so that we have a way to show that wall without completely blocking out that cell, because we need that information because that's the robot's goal location. And this is why we also have a way of representing a world known as topological mapping. Topological mapping, as it sounds like, basically is the topology of the world where each cell gets a number between 0 and 15. And this is based upon the binary counting process. So basically, if there's a 0, there are no walls around that cell. If there's a 1, there's one wall on the north side of that cell. If there's a 2, there's a wall on the east side of the cell. If there's a 3, there's walls on the north and east. If there's a 4, there's a wall on the south side of the cell. If there's a 5, there's a wall on the north and south side of the cell, and so on. If there's a 15, that means that every wall is occupied, and that would be like a 99 in our occupancy grid. So 0 and 15 would be the two that you would use for an occupancy grid. You will find sometimes some students will take a topological map, scale it into a 4x4 for each cell, and turn it into an occupancy grid. I don't really tell you how to do the final project, so it's ultimately your choice. You could keep it as a topological map. You could change it to an occupancy grid. You can go one way or the other, but it's your choice. So here's an example of that artificial world that we showed before, except now it's represented with topological map encoding, where you see the completely occupied areas now have 15s, and where we had that wall right here is now represented with 2, 6, showing that there is a wall on the east side, and 9, 12, showing that there's a wall on the west side. There's also a 6 and a 12 down here because there's walls at the south side. So our next process after representing the map is extracting features from the world. This will become important when you do localization. So for example, you will use the robot sensor data, and you can do this with either the 4IR, the sonar, or any combination of the IR and the sonar. But you want to have a way to encode whether the robot is currently in a hallway, if it's in a T-junction, if it's in the T-junction facing north, south, east, or west, if it's in a dead end, if it's in diagonal in a corner, etc. You want to have a way of representing these nodes, and this now gives you at least one way that you can do path following. You could tell the robot to move through a world where it goes from a dead end to a T-junction to a dead end. That tells you that the robot is here, here, and here, or at the north side, here, here, and here. It's also another way for you to do localization, because if you now can take your map and you can extract these features, then based upon that and the robot's orientation, you should be able to tell me that the robot is in a north, south, or east corner, or it is in a hallway in the middle, etc. So feature extraction is also very important. So once again, odometry error and sensor error are still in play for all of these. So always be thinking about how can you handle that in the midst of this. So the first kind of path following that we do is called topological. And it is the most basic, but it helps us to get started. And that just means that distinctive places in the world are where the robot makes a decision. A distinctive place could be a dead end, a corner, a hallway, or a T-junction. So now we give the robot a path to follow completely based upon the topology of the world. So S would be start, T would be terminate. So in this case, the robot's command would be start, right, left, terminate. And that essentially means turn right at the first opening, turn left at the next opening, and stop when you get to the dead end. It's a way to quickly tell the robot how to get from one place to the other based upon where it makes decisions in the world. And here is an example of a team using this.
The hallway, and let's hope she sees the right gateway and makes a turn. Will Lisa make her go? Will Lisa make her go? I think she will. Will she head in? Will she recognize the corner and terminate? This is Marge, Matt, and Trenton doing topological path following on Thursday, April 14th, 2011. The path is left, left, right, terminate.
Do it. Go down the tree.
Marge is doing left wall following. Is there any follow center behavior, young men?
Yes. Whatever.
So when it gets in a hallway, it will follow down the center of the hall? It's going to try to center itself? PD control?
Oh, look, it's doing it. It's on. Oh. Boom. It still made the turn. No, she's gonna stop. Gas.
Are you on track? Good job.
Okay, we will show one more example of topological path following, and this is where we will end part 1 of the final project recitation. Please come back for part 2.
This is our GUI for the other topological world. It's going to go start, right, left, and terminate. So it's going to start, go right, left, and then go over there.
So this is a path following video. We want to go from here to there. So it's right, left, right, left. And it's R,
Alright, shithead. Just see if you're excuse me. Let's wait. I can shoot over here.
Oh, is it the same set of gate?
For long enough.
For long enough, yeah, you're not wrong.
cool. Okay, Ronin is now control. Is now control.
That is a significant improvement.
It goes by itself.
Still finding space in the wall.
Now it's actually following the hallway. Now we just need to find out me.
And it will stop.